Thank you very much for the introduction. Thanks a lot for the invitation. It's a great pleasure to be here and start the lectures in this Abel symposium. I hope it's not written too small for the people in the last row. Is it okay? Anyway, I will speak, and I hope I speak loud enough for everybody to hear. So today's lecture on my part will be about long-time behavior of classical systems, and we shall see several examples of such systems. It will not be, of course, any classical system, but some systems coming from various parts of science. Large-time behavior in general is a quite important problem. First, because you want to predict observations, what will happen after a certain time. And if a behavior is unstable, that is, maybe something happens but very quickly it will change, you may not be able to observe it. If it is stable in the large time, then you will be able to observe it if the model is realistic. Also, often when you are handling models coming from realistic systems, it's so complicated that you cannot compute or estimate what will occur, except if you use numerical simulations maybe. If you want to say something interesting and you can determine what is a large-time behavior, at least you have something. However, this is difficult even for classical systems. And in this lecture, I will only consider systems obeying laws of classical mechanics. The oldest of all problems of mathematical physics about the long-time behavior probably is the stability of the solar system, which has been studied by many people. Recall that around 1600, the Kepler laws allowed people to give a good description of the elliptic orbits of planets around the sun, planets of the solar system. And we still learn these laws in school today. However, about 24 years later, Newton published the law of universal attraction, gravity, and he found that with this he can derive the laws of Kepler with a more fundamental approach based on only one law. The law being that if you have two bodies with given mass, then of course there is a force which is exerted by one on the other, which is like proportional to the inverse of the square distance and proportional to the product of the masses. Okay. Does anybody see the pointer? Let's use the... Yes, that was a good trick, thank you. Okay. At the same time, Newton manages to write down the equations for point masses. Let us reduce the planets to just points, and these points will be the positions of the planets at time t. Let's assume we are in Euclidean space, which is three-dimensional space. This is physics before the general relativity and so on. And we have the mass of any planet. We give numbers to these various bodies. Maybe the Sun is number 1, Mercury is number 2, etc. And then you can write the equation, which is derived from the usual Newton identity, that the force is the mass times the acceleration. If you have just two bodies, you recover the Kepler laws. If you have more than two, Newton understands that you cannot find an exact solution, then what to do? And from that moment, when Newton wrote the equations and understood he could not solve it for more than two bodies, and understood the trajectories would not be elliptical but approximately elliptic, and in particular would not be closed, starts the problem of the stability of solar system. You take a solar system and you start it with initial conditions satisfying this or that. What do you get in the long range? This can be considered as a more general problem, of course, in which is not necessarily the gravity which is at work, but some other force may be coming from some potential, interaction potential, let's say two bodies. What do the trajectories look like as t goes to infinity? If you look at the solar system, in first approximation, of course, it's just the sun, and the rest is a bit of perturbation, some small mass. Of course, very important to us, but not so important for the whole, it might be argued. If you look at all the Jupiter and all the planets, it's like about 1,000th of the mass of the Sun. So this looks like good news because in first approximation, when you write the Newton equations, the contribution of the Sun will be much larger than the other contributions. And it's like only the force which is exerted between the Sun and the planets will count. However, even if the deviation is about 1,000th, in the long run, it should play an important role. If your bank account loses 1,000th every day, after 1,000 days, you are in trouble. And it might be the same with the Sun. And so Newton understands that with these laws, there should be a chance that after about 1,000 years, the Sun would have an important perturbation. The solar system would have an important perturbation. Since this happens to not be the case, we know from records and so on that solar system has been more or less how we know it for more than 1,000 years. He concludes that there must be some divine protection on the solar system which has to be added to the equations. It was the start of a famous philosophical debate. So later arrived somebody who played an important role in Russian mathematics, of course, Euler, and also Lagrange, Laplace. In the 18th century, they understood that the initial intuition of Newton was quite not true, and that even if the perturbation is of the order of 10 to the minus 3, the solar system enjoys stability over times which are of the order of 1 over epsilon square, at least. This is a mathematical result, quite remarkable. At the same time, they understood at the end of the 18th century that all of the astronomic observations made at this time could be explained by using only the Newton law. This was an important moment for the history of sciences. If you still think what it is 1 over epsilon square in practice, well, it's the order of the million years now. And it's remarkable that at the time they understood that you can qualitatively predict some stability effect for the solar system over the time scale that were extremely large, million years scale. It was the beginning of a long story with many surprises. Later, Poincaré, after thinking that he could improve the stability theorem and show the stability over infinite times most of the time, showed that in fact there is a possibility of instability. This was the discovery of the phenomenon of homoclinic intersections. This was the start of many researches that would lead to chaos theory, ergodic theory, etc., modern theory of dynamical systems. At first, Poincaré was interested in this example of the solar system or a simplified version thereof. And then, about 50 years later or so, another enormous surprise when Kolmogorov, so this was his 1954 paper, had the intuition that a slightly perturbed integrable system, okay, has to be Hamiltonian, etc., and some conditions which I will not describe, but under some conditions, an integrable system that you perturb slightly will remain most often quasi-integrable. Meaning that if you start from the Kepler view in which the planets interact only with the Sun, and this you can completely integrate, and these are the Kepler formulas, and you had this slight perturbation with epsilon that would be very, very small, then for most initial conditions, nearby some initial condition, for most of them, the system will behave, trajectories will remain like a distortion of the trajectories of the initial system. And in particular, you will have stability for all times, and you know that never, most of the time, it will never occur that two planets, for instance, bump into each other, or that one planet is lost, etc. This was a blow, and for a long time people started to think again that solar system is quite stable, until in the 80s, 90s, numeric evidence arrived of chaotic behavior in the solar system over time scales which are not much larger than the stability time scale. The last results from a couple of years ago suggest that solar system is very badly predictable after about 60 million years. So in the 18th century, they knew that there was stability around 1 million years, and now we know there is instability at time scale of about 60 million years. This was the story of the solar system. From that example emerged several thoughts, several ideas, several paradigms that reshaped the view that we have of physics and dynamical systems in the long run. The concept of ergodicity, which I mentioned, first appeared in the work of Boltzmann, was developed and in gestation in the work of Poincaré, more explicitly in the work of Birkhoff. The idea that when you have a classical mechanical system and you want to know how it behaves in the long run, you start by listing the restrictions which are built in, like conservation laws and so on, like the laws which apply to the system. And if all the admissible phase space can be attained, admissible being not forbidden by conservation laws, then you may replace large time averages by phase space averages with respect to some equilibrium measure. And you will have a behavior that even if you don't know exactly where the trajectory will be in the long time after such a time, you know that it will visit every possibility according to a certain distribution of probability. This was the idea of ergodicity. And at the opposite of ergodicity in some sense, there are some situations in which you know that it will not happen that the system visits everything that is available. On the contrary, it will restrict itself, like doing some kind of self-censorship, and remain close to a behavior which has no reason to be followed. And that is what I described. So the names attached to the theory are Kolmogorov, Arnold, and Moser. Take a completely integrable classical conservative Hamiltonian system, perturb it by adding a small, possibly non-integrable interaction of a very small size, and then with a very large probability, and if you take epsilon to be very, very small, probability will be very, very large, the system will remain stable for all times, and it will be a deformed quasi-periodic motion, quasi-periodicity being the integrable case when each planet orbits around the sun and each planet defines a certain frequency, and if you look at the vector of the positions of the planet, this is a quasi-periodic system. Does it apply to the real world is an interesting question. Ergodicity works better if the system is well mixing. This comes in the theory, this comes in practice. And there are extremely few realistic systems which are known to be ergodic. There are many model systems and so on, but in real life, if you have which system do we know to be ergodic, there are very few. And many are known to be not ergodic. Kolmogorov-Arnold Moser shows that even if the conservation laws do not prevent erratic or catastrophic behavior, sometimes those will hardly ever happen. And this is a very important conclusion. This completely changed the way we think of dynamical systems. But the Kolmogorov-Arnold Moser, in practice, neither applies to real systems, never. Because the perturbations are not small enough. The epsilon in the Kolmogorov-Arnold Moser theory has to be so small that in practice, being for real solar system or for other mechanical systems, it doesn't apply. I mean, if you look at the mathematical statement and look at the epsilon and try to match, in practice it will never work. So this is an interesting situation from the point of view of epistemology. We have two major concepts which change the way that we see physics. Neither of these contexts applies in practice. And still it was a revolution in our understanding of of the world around us, for mathematicians and for physicists. Now, what about the stability of a galaxy or a gas or a plasma? In a galaxy, you may have 100 billions of stars. Look what big complication it was for just one sun and 9 planets, or 10, it depends what you count. And then you can think, with 100 billions, what on earth are we going to do? The first thing to realize is that there is no way you can export Kolmogorov-Arnold Moser theory directly to this case. If you look at the theory and how it behaves, the dependence on the constants on the dimension is a disaster. If you increase and increase the number of bodies, your epsilon, which was already monsterly small, will become essentially zero. Then we have to turn to another formalism and appeal to the many-body scientific revolution in about 1865 to 1875, led by the physicists Maxwell and Boltzmann. It was an extremely important revolution with a major modeling advance, the Boltzmann equation, major mathematical advance, which was the notion of statistical entropy, major physical advance, which was the concept of macroscopic irreversibility, and a major advance in partial differential equations, study of large time limit using a natural Lyapunov functional. Some outcomes of the revolution were the explanation by Einstein and by Smoluchowski of the Brownian motion, the evidence for atoms, which was laid out by Perrin around 1910, 1912, gathering evidence from previous experiments, and it's only from that moment that people were really convinced of the existence of the atoms. The principle of macroscopic equations deriving from microscopic models put forward by Boltzmann, and the basis for equilibrium statistical mechanics with Gibbs. It was later adapted to all kinds of physics, relativistic, quantum, etc., but this revolution took place in the classical world. With a monster influence on mathematicians, as we can see by some quotes, for instance, with Sommerfeld here, mentioning a debate and saying all of us younger mathematicians stood by Boltzmann's side. It was a mathematician speaking. Hilbert was inspired by Boltzmann to write his sixth problem about going from the laws of the atomistic world to the continuous laws of partial differential equations. Katz in 1959 mentioned the Boltzmann treatise as one of the greatest books in the history of exact sciences. So it had an important influence in physics and in mathematics. If we can say a few words about how it is related to concepts of determinism and probability. It has been a classical theme since Bernoulli, Laplace, Polya, and others to look at the statistical behavior of many random quantities when the number of random variables goes to infinity. And look, for instance, of course, at the average. This field also has been early on adapted to social and natural sciences, in fact, even before it was adapted to physical sciences. Basic principle, of course, is that the statistical behavior of a crowd of n particles is well predictable if the individual behaviors are chaotic and uncorrelated. Uncorrelation is the key. And here we arrive at the molecular chaos assumption of Boltzmann. Any two particles among the crowd should be uncorrelated or almost uncorrelated. It is this uncorrelation at the microscopic level for the many-body system that will allow a deterministic evolution of the particle density. Just as law of large numbers or the Gaussian law of errors works well if you have independent experiments. If you have correlations at the microscopic level, some more determinism at the microscopic level, it will be very bad news for the macroscopic level. A new scientific paradigm emerges from that time. Do not study the many-body problem because it's too difficult and it's useless. Instead, under a chaos assumption, that is uncorrelation, establish an equation on the density of particles. This step takes advantage of the large number of particles, rather than the large number of particles being a disadvantage. Once you have this, you study the equation, which of course is interesting in itself, and establish its long-time behavior. The idea being that if you have so many particles, it will look continuous, like a fluid. Like a fluid. I will show you the numerical simulation a bit later, maybe. But when you look at numerical simulations of, for instance, a galaxy, when it is sped up and you look at over time scales of millions or billions years, you don't have the impression that you look at stars which are attracting each other. You have the impression that you see some kind of fluid which is moving and regions of high or low density are created or destroyed. This is governed by the Newton equation, but it looks like a fluid. Keep Kinetic theory is the system mathematical modeling adapted for this. You describe a classical system by means of the density of particles in phase space being positions and velocity. And this distribution, you wonder how it will vary according to time. This is an example of some kind of any distribution. This is a very particular one, the Gaussian distribution, which we know from probability theory to be important in many situations. Here is the crucial Boltzmann step of going from the microscopic to the macroscopic in the simplest situation of mean-field interaction, not the one that Boltzmann was considering initially. And with this process, you will go from many, many simple equations for positions and velocities to one equation that will be somewhat complicated. Here, the unknowns are all the positions and velocities, and maybe there are 100 billions of unknowns. Here, the unknown will be the time-dependent probability measure. And at each time t, this probability measure tells you what is a fraction of the mass which at time t lies within a certain region of phase space. The formal rule to go from here to here is that in the equation, whenever you have a summation over all the particles, or maybe an average, you will replace this by an average in terms of measure theory with respect to this measure mu, depending on time. So for instance, if I want to compute at point x the potential, the gravitational potential, which is created by all the other stars or all the other planets, I will replace this discrete sum by the continuous sum with respect to the probability measure mu t. Let us, from this, write the equation. If you apply the rule which I just said, and start from the Newton equations, in which every particle is attracted by all the others, and pass to the limit by using this rule, you end up with the so-called Vlasov equation. The time derivative of f plus the convective term in which you the transport term in which you have the scalar product of the velocity and the x gradient of f, plus the scalar product of the force, instantaneous force at time t and position x by the v gradient of f is equal to 0. And the force is related to distribution f by a double integral, or if you want, by a convolution type formula, involving the gradient of the potential in space and the distribution function. Because f is in linear dependence to the distribution f, this term here is quadratic in f, and you have a nonlinear evolution equation. This is the basic formula that you find at the beginning of any kinetic treatment of plasmas or galaxies in the corresponding books. It is universal model, well accepted. Let me emphasize that its rigorous justification is still open. Formally, you can do it in a few lines. You can even explain this almost to high school students once he knows what the chain rule is. But it is still open for rigorous justification because the real life potentials have a singularity, like 1/r in dimension 3 for gravitation or electric interaction. If the potential is smooth, this was done a long time ago, in particular by Dobrushin and other people, and you can derive it very easily. If the interaction is singular, we still don't know how to do it. A more elaborate model than this mean field is the Boltzmann approximation. Mean field is each particle interacts with everybody. Boltzmann approximation is to add the effect of collisions. Sometimes some particles will pass very close to you, and this will result in some major problem, maybe a shock or some strong interaction, an interaction between two particles that may be significant on a time scale which is lower than the mean times on the spatial scale, which is smaller than the spatial scale given by the mean density. These collisions or close encounters, the idea of Boltzmann was to model them in some kind of random process, assuming again molecular chaos, that particles are uncorrelated before collisions. Maybe you will bump into somebody, but you didn't know it, didn't know him, didn't notice him before the collision. After the collision, of course, there will be some correlation. You have bumped into him or her, but before, no correlation. These additional collisions will add a term in the equation which also will be a quadratic term, an interaction term. This is the Boltzmann collision operator. And it tells you about the variation in the density function which is due to these collisions. And it takes the form of a double integral. Let's say this integral is about all the possible velocities of somebody that you encounter, and this integral is about the parameters of the encounter. Maybe the orientation in the encounter is like this, or like this, or like this, or like this. There should be some direction playing a role, and that's the meaning of this extra integral. And you see it is quadratic. This is because you are considering the effect of particles on particles. It takes the form of a product, like it's some kind of tensor product. You see in the velocity variable, this comes from this uncorrelation. When we know two random variables are uncorrelated, then the corresponding distribution function is a tensor product. However, it is not really a tensor product. It's only a tensor product here in the variable of the velocity. But at the position, it is not, because it's the same position here and here, because in this model, you only encounter people that are very, very close to you. This is the source of major mathematical difficulties and a main reason why, to this day, we are still unable to construct in full generality classical solutions of the corresponding Boltzmann equation. The kernel here, B, reflects the interaction. Depending on the interaction, some collisions parameters may be more likely than others. If you have a model of hard spheres, like a big billiard, this was what was in the head of Boltzmann in particular, it will have a simple form like the scalar product of the relative velocity at the encounter by the parameter omega. It may have an angular singularity, and this has been the source of many works. It may have a kinetic singularity, and there is a whole zoology about this and many interesting effects, which I will not talk about today. The Boltzmann approximation is conceptually important. First, because this is a way to derive familiar laws, like how a gas evolves, from first principles. Even more than that, it's an example in which you hope to order the reality into boxes. This is a problem that is much beyond fluid mechanics. It's a general problem in physics or in science or even in other fields of knowledge. That even if you know that the matter is made of atoms, etc., for many purposes you don't want to think of me and the atmosphere, etc., as collections of atoms. You want to think of it as various boxes and look at the interaction between these boxes. And maybe there is some gas, and then there is something here, etc., and you want to be able to transform a world in which there are many, many, many elements into a reduced version in which there is interaction of this with that, etc. It is related to influential historical disputes, which I will comment upon briefly. It is still open, this Boltzmann approximation, for most dissipative equations, even the heat equation. And let me recall that to this day, we are unable to justify the basic heat equation that is one of the first equations that we encounter in the study of partial differential equations from first principles. We all believe it is a good description of what happens if you take some metal, for instance, and heat something and look how the heat is transformed, but nobody is able to do this from an atomistic view. One key concept behind this is a molecular chaos, that there would be no correlations between particles. However, as I just told you, when particles encounter, correlations will be created. So the correct notion is not really chaos, but one-sided chaos. On pre-collisional configurations, no correlations, but just after that, there will be correlations. It is not clear in which sense precisely it would be correlation. All this, whatever it is, this one-sided chaos should be preserved in time. If you start at initial time with this one-dimensional chaos, one-directional chaos, it should be preserved. And it should be justified that this is preserved, although correlations continuously form by interactions. This is tricky. We still don't know how to do it in a satisfactory way. It has been 100 years of controversy. The guy who solved the dispute is Oscar Lanford. He passed away sadly, just a few months ago. And maybe he is the guy who proved the single most important result in the theory of, maybe in all statistical mechanics, it can be argued. He showed how to rigorously derive the Boltzmann equation from Newtonian mechanics of n hard spheres of radius r in the scaling when n r squares goes to 1, n goes to infinity, r goes to 1. This means many, many very small particles. And he did this on a short time interval, assuming strong molecular chaos at initial time. His proof has been rewritten and adapted by many people. It's a work that continues to this day. And it was so important because it solved this controversy and showed that you can have equations, you can have microscopic equations forming a reversible system and end up at macroscopic level with an irreversible equation like the Boltzmann equation, and order these many particles into one equation. It leaves many open issues like how to deal with long-range interactions, large times, how to find a satisfactory non-trajectorial proof, what is the propagation of one-sided chaos. All these questions are still open, are still huge open problems in statistical mechanics. Mm-hmm. What does my computer decide to do? Mm-hmm. Okay, Boltzmann and Vlasov equations are the pillars of kinetic theory. It can be argued. They are used in many applications by engineers, by people who study the stars, by people who study plasmas. They are at the same time beautiful mathematical objects and extremely useful objects. What do we do when we have the equations, assuming we have them? Starts the mathematical analysis of the kinetic equations, in this case pioneered by people such as Kahneman, Katz, and Grad. Now it is rather okay for Vlasov, still a mystery for Boltzmann, except in some particular situations like spatially homogeneous or perturbative. Meaning by rather okay, I mean showing good theorems of existence, uniqueness, etc. Still, what about the long-time behavior? So this is the sequel of the program. The analysis starts with the Boltzmann great discovery, the entropy. Of course, when you do a statistical description of matter, it is less precise than if you have the microscopic description with all the positions and velocities of all atoms. So each macroscopic state that you observe corresponds to some microscopic uncertainty W, the number of possibilities associated to your observation. And this is the basis of the Boltzmann formula for the entropy. S is k log W, k is the constant, and you take the logarithm of the number of possible states or the volume of possible states if you are in a continuous description. Boltzmann's H theorem is of several parts, consists of several parts. First, if you apply this general formula, S is k log W, to the case in which the macroscopic system is a probability distribution F, then you compute S. The correct notion is minus integral of F log F. This is the entropy of Boltzmann. And second, if you plug this thing in the equation, you discover that it can only increase with time, never decrease. And you can compute the time derivative to be a big quantity, which is obviously non-negative because it's the integral of something which is non-negative. Because a minus b times log a over b is always non-negative. If moreover you ask, when does this entropy variation vanish, you see that it will only vanish for some Gaussian distributions. And this is a beautiful moment in which Boltzmann was able to make the connection with theory of gas and classical probability theory, showing that the Gaussian appears naturally in kinetic theory of gases as in probability theory. Entropy, as I explained, measures the volume of microstates associated to some degree of accuracy in macroscopic observables to a given macroscopic configuration. It tells us about how exceptional is the observed configuration. This is not the only notion of entropy, the one of Boltzmann. There is the Shannon entropy associated with coding and communication, for which the formula is the same as that of Boltzmann. There is the Kolmogorov-Sinai entropy. There is also the Kolmogorov complexity. All these are three different formulas, but all have the same general philosophy about how difficult it is to describe a system given some information that we have. Entropy is an entropy context. This is a pun, playing on words, but it's also here to remind us that entropy depends on our scale and what kind of experiments you can do and measure. If you measure the entropy at our scale, it will not be the same as if some very tiny being would measure the entropy. In particular, it makes no meaning to ask, for instance, what is the amount of entropy in the Earth or in the solar system. It depends on your description, it depends on the mathematical model. It's not like notion of energy that in some sense would be contained in some system. Entropy depends on the description, it is partly in the eye of the observer. This is me with the great man, Boltzmann, and the big formula. And this picture was taken in the Zentralfriedhof in Vienna in 2005, I guess, 2005 or 2006. 2006, for the 100th year of the death of Boltzmann, who tragically committed suicide. So, as I explained, Boltzmann showed how to go from k log w to minus integral of f log f. This formula here is very important. Conceptually, it is at least at the same level as the famous E equals mc square of Einstein. And but however, it is impossible to apply in practice. How do you compute w? So it's very important that Boltzmann gave us the recipe that you can use as an engineer, like to compute in practice from F, the entropy. How to go from this formula to this formula is a famous elementary computation. Take n particles in k boxes, take some rational frequencies, f1, etc., fk, so that the sum would be 1, and call nj the number of particles in the box number j. And you ask what is the number of configuration such that in real life the frequency that you observe corresponds to the frequency that you determined a priori before. If, of course, for instance, the vector of frequencies is in anything but 1, 1, then there is only one possibility, which is to put all the balls in the corresponding box. If you have 3/4, 1/4, and you have 8 boxes, and you ask what is the number of possibilities to put 8 balls such that there is 6 here and 2 here, and of course it's the elementary combinatory exercise. And more generally, you have the formula which is given by the ratio of n factorial by the products of the nj factorials, which gives you the number of possibilities to do so. Once you have this is your w. To apply the Boltzmann formula, you take the logarithm and you pass to the limit as n goes to infinity. And if you do a bit of analysis, for instance with Stirling's formula, although it's not the only possibility, you will find that 1 over n times the logarithm of the number of possibilities behaves like minus the sum of fj log fj. This you should think of as like k log w. And this is the key to obtaining this general formula by Boltzmann. This is also the most basic instance of what is known in probability theory or statistics as Sanoff's theorem of large deviations for observing the empirical measure associated to some random distribution. As I said, the Boltzmann entropy is distinct from Sinai-Kolmogorov or Kolmogorov complexity, although those are also about the possibility to describe a system and coincides with the Shannon entropy in theory of communication. This is a quote by Shannon, by the way. I thought of calling this quantity information, but the word was overly used, so I decided to call it uncertainty. When I discussed it with John von Neumann, he had a better idea. You should call it entropy for two reasons. In first place, your uncertainty has been used in statistical mechanics under that name, so it already has a name. In second place, and more important, no one knows what entropy really is. So in a debate, you will always have the advantage. Entropy, in spite of this kind of curse given on it by nasty von Neumann, has many faces and has proved tremendously influential in mathematics. It is fundamental in compressible fluid mechanics, for instance, to select relevant solutions, a key element of information theory. It also plays a role in deriving quantitative versions of the central limit theorem. It was instrumental in the celebrated proof by Nash of the continuity of solutions of linear diffusion equations with non-smooth coefficients. It also played a key role in the Perelman proof of the Poincaré conjecture. That was not the only ingredient, of course, but it was important at some point to use an entropy with a resemblance, important resemblance to the Boltzmann entropy. It was used by Varadhan and collaborators and Yao, this is Hans-Serg Yao, for infinite dimensional hydrodynamic problems. It was used also very far away from statistical mechanics by Voiculescu in his work on the classification of 2-1 factors in the theory of von Neumann algebras. It is also, more recently, the basis of the definition of the heat equation in metric measure spaces. How do you find the heat equation in a very general setting in which you don't have even a gradient, for instance? These are works in which I participated over the last few years related to optimal transport. Boltzmann's irreversibility is very striking. Entropy increase, however, the Newtonian mechanics is reversible. If you watch a movie of Newtonian mechanics, like a classical billiard game, if there is no friction, you can pass the movie forward or backward, you will see the same. It's the same laws of physics. This is why people like Oswald, Loschmidt, Zermelo, or Poincaré question the Boltzmann argument. Should be impossible to go from reversible microscopic dynamics to irreversible. And it's exemplified by this theorem of Poincaré, that if you start with all the particles in one half of the box and let it evolve, then after some time, all the particles will be back in the initial ball, in the initial half box. And it's a respectable theorem that you can prove easily, the Poincaré recurrence theorem. This with probability 1. And of course, there is a point which was obtained by Boltzmann and the others. This will never, ever happen. It may happen, but over time scales which are so terrifying that the laws of physics are not valid on such a time scale. Of course, we are doing classical mechanics. How do you expect it to behave on time scales of billions of billion years, and so on? Instead, what happens is that most probably, with outstanding probability, the gas will invade the whole box. And it is what we observe. Why will it do so? We like to think that there is a force that the void attracts particles like it's aspiring, sucking particles in. But Boltzmann tells us it's not this. You have to think about it like just the effect of these random collisions and the fact that the gas will try to maximize its entropy and have a disorder which is maximum. What does it mean, maximize the entropy? Well, in this configuration, the disorder is higher than in the initial configuration. Instead of being all neatly in a half box, they may be anywhere. It's more difficult to get the behavior of one particle. So there is more entropy here. And that's the explanation given in the Boltzmann for this long time behavior. Then you may say, if it's just a statistical thing, it may be sometimes true, sometimes false, not always. Then Boltzmann will tell you it is always true because of the terrifying numbers which are involved. To give you an idea, and this shows you the power of combinatorics, not only do large numbers occur here, but they occur in combinatoristic formula, in combinatorial formulas, making them even much larger. if you go from the configuration in which the gas is in a half box to the configuration in which the gas is in the whole box, the entropy goes up by log 2. It's like there is one information more that you need to know whether the gas particle is on the left or on the right. Okay, log 2, why not? But assume you have 10 to the 17 particles in your box, which is quite reasonable. Then the volume of microstates is 2 to the 10 to the 17 larger in the second instance than in the first instance. Now, 10 to the 17 is large, but 2 to the 10 to the 17 is out of this world. If you want to compare this ratio of volumes to things like the ratio of the volume of the whole galaxy to the volume of the proton, you find that this number is much, much, much smaller than this one. In fact, you would need to get a more realistic approximation. Imagine you take one proton in the galaxy, then expand the proton to the whole galaxy size, take another proton inside this expanded proton, and repeat the process 300,000 billion times. And then you will have an idea of how large this is. When you are in front of such numbers, it's not something that is likely, becomes certain. Now let us compare the qualitative behaviors of these partial differential equations, which I explained, the Vlasov and the Boltzmann. In Vlasov, just you take into account the behavior, the interaction of particles with all the other particles. In Boltzmann, you add the effect of collisions. Vlasov is time reversible like the Newtonian dynamics. Boltzmann is not because of the entropy. The energy is conserved in both systems, but the major difference is that in Vlasov the entropy is constant, as you can derive from the Liouville theorem, while in the Boltzmann case the entropy increases, as you can see from the Boltzmann theorem. And in the Vlasov case, there is a very, very large number of possible equilibria. In fact, it's an infinite dimensional space of equilibria. For instance, any distribution which depends only on the velocity is an equilibrium. On the other hand, in the Boltzmann case, there are only Gaussian equilibria, as we understood from the study of the entropy. So you see on the right, the behavior looks predictable. On the left, not at all. And it's tempting to believe that in the right case, we are in a situation so that we can integrate and find the behavior in the end. On the left-hand side, it should be something chaotic or whatever, with no particular behavior that we can predict. This was kind of the view for some time after the basic equations were written. And the idea that entropy increase is what stabilizes the system, and that without this, there is something like instability. Let's skip this and arrive directly at this. 1946. This is Lev Landau. He doesn't look happy, of course. This is when he was sent to prison for no good reason. And in 1946, after he was out of prison, he makes this amazing discovery. I took the amazing discovery words from a textbook of that time. Landau linearized the Vlasov equation around F0 of V, some equilibrium. And for entire analytic data, he shows that for this equation, the force often will damp to zero as time goes to infinity. So he finds some stabilizing phenomenon by looking at the linearized equation. In his paper, which is striking, he starts by explaining that almost all the results of people who worked on this are false. He gives a formula for the rate of decay, which I write it. You don't care about the exact shape of the formula, but he says the rate of decay for the linearized equation is this. It's obtained by the solution of some equation involving complex numbers, and the infimum of some real parts of some complex numbers, etc. This has been called since then the Landau damping, the idea that the force may damp in a system even if the entropy is constant and there is no stabilizing effect of the type of Boltzmann. This was the start of the problem of the long-time behavior of Vlasov equation. In this Landau picture, perturbations may damp away spontaneously in an apparently irreversible way and thus may be approached to equilibrium. This has been much discussed since then. It is well accepted and observed, in particular in astrophysics, that the corresponding equations will relax in a short time, short meaning before entropy increases. If you look at a galaxy like Milky Way or whatever, on the relevant time scale, there will not be any significant increase of entropy in a particle description of that galaxy. However, it is observed in numerical simulations and well accepted that there will be some stabilization of the galaxy on a time scale which is observable. This was formalized by astrophysicists like Lyndon Bell, and there were attempts of theory by Robert and Miller, etc., all based on static approaches, saying, okay, let's maximize entropy and so on. However, no one for the moment has any theoretical explanation based on dynamics for this short time relaxation, which is called often in astrophysics violent relaxation, and that nobody really knows what it is, but except to concur that it does occur. And the Landau damping perturbative effect, even though it is expected to be only in a perturbative regime because it was obtained by linearization, thus has a lot of conceptual importance as a possible way to enter the otherwise wide open field of relaxation for entropy preserving system. If you don't have the entropy stabilization, how do we have stabilization? Another thing which is a problem is the linearization reasonable? Landau based his observation, his reasoning, on the linearization. So he started from some equilibrium, say stable, added a perturbation, and looked at the resulting distribution function. And he let it evolve by the nonlinear Vlasov equation, which is the one I wrote before. If you linearize, it means that you take the quadratic term out and keep only the linear terms. And why not? Because the quadratic term, of course, is much smaller. This, however, if you look at the equation, seems very natural if this term is small with respect to this one. But you can see from the linear analysis that you don't expect this term to remain small with respect to this one. On the contrary, this term should grow in time like linearly in time. So even if it is very small initially, if you wait long enough, it will be much larger. And you arrive at the tricky situation in which you seem to be neglecting a term which is much larger than the term that you keep. This said Bacchus as soon as 1960. In this paper, first he established rigorously he put the reasoning of Landau on mathematically rigorous basis and for the linearized equation. At the same time, notice that this problem seems to destroy the validity of the linear theory. There is a natural nonlinear time scale on this problem, which is 1 over square root of epsilon. This makes you wonder, you know, even if I start close to equilibrium, of course for a short time it will remain close to equilibrium, but over a long time, maybe small perturbations combined over a long time will lead you into the nonlinear regime. Not because you started far from equilibrium, but because you wait for a long time and you don't have any mechanism keeping you any low, keeping you close to equilibrium like it would be for the Boltzmann equation. If you look at this from just the point of view of analysis of PDE, you notice that when we linearize, we neglect a dominant order term. First order derivative in V, and there is no other term which is derivation in V for the unknown H. This can be very bad. Maybe it changes your behavior completely. The linearization at physical level removes the entropy conservation, so maybe it's different physics. In fact, it was argued by Izychenko in a paper of 1997 that the approach to equilibrium should be very slow for the nonlinear equation, while it is very fast for the linearized equation. And almost at the same time, this was kind of contradicted by Cagliotti-Maffei, constructing some non-trivial solutions decaying exponentially fast. In such a situation, in which even on the physics side there is controversy, you can hope that mathematical reasoning will sort out the mess and tell you which is the right answer, at least from the theory. In 2009, with Clément Mouot, we solved this problem, in a sense. We considered a periodic system and the interaction potential W, which is no more singular than the Newton potential. Take a linearly stable, analytic, homogeneous equilibrium. Analyticity is the same assumption as Landau. I will come back on this later. Linearly stable, of course, is what you want to treat. And take an analytic initial datum which is close to F0, solve the corresponding Vlasov equation. Then the force decays exponentially fast to 0. So the Landau damping does hold true for the nonlinear Vlasov equation. Some mathematical comment. First, not only does the force go to 0, but we also prove that the distribution itself converges to some equilibrium. This equilibrium, in general, will be different in large negative time or in large positive time, but will exist in both directions of time. And there is no recipe for this equilibrium. It is not a maximum of entropy. And in fact, you can show that there is no recipe in the sense that even though the initial datum, starting from initial datum, going in large positive time or in large negative times, you may have different equilibria, which would be impossible if it would be derived by a universal recipe. This is given by a quantitative estimate. And besides confinement, which is very important, so we put the system in a periodic box, not only the proof would not work, but the result would be false if it would be in the whole space. And the mixing, which is also a key. Another key in the study is regularity. And basically, so to speak, the picture which emerges from the proof and also the intuition is that Landau damping is a relaxation by mixing in which the regularity is the key for the estimating the role of the mixing, and it has to be confined. These are the three key words: confinement, mixing, regularity. Since then, a simplified proof, at least for parts of the proof, has been written down by Bedrosian, Masmoudi, and Mouot. Some of the physical comments. How do we resolve the paradox between the reversible equation and the irreversible behavior? The resolution is that information goes to small velocity scales where it becomes invisible. In a way, it vanishes into thin air. There are oscillations in the distribution function which become more and more fast in the velocity variable, and these oscillations become so fast at some point that you cannot measure them, and this is where the information disappears. And this is why the convergence here is only weak convergence, not a strong convergence. This picture was, if you look at the literature, was already understood qualitatively by some people and is still not understood by some others, depending which papers you read. Lynden-Bell wrote this, which is very well said. A galactic system whose density has achieved a steady state will have information about its birth still stored in the peculiar velocities of its stars. Peculiar velocities meaning the velocities of the stars, their precise distribution, something that you don't have access to because when you feel the force exerted by a star, you feel only the position, not the velocity. Here is numerical illustration. If I start from this perturbation of the equilibrium and I let it evolve after some time, I will have a picture like this. This looks like quantum diffraction or whatever, but this is classical mechanics. And this is for the distribution function, the velocity variation, velocity distribution of the particles in your plasma. This is a picture of the variation of the electric energy as time goes, and this is in logarithmic scale. Look how the energy goes. The electric energy, so this is only the part of the energy which corresponds to the position variations. and so the electric, if you want, because of course, again, in the electric energy, you don't have the velocity dependence. The velocity dependence appears only in the kinetic energy. Look how it goes. You have these variations over a certain time scale, and there is a global tendency for the electric energy to decrease like exponentially. This is the same picture for gravitational interaction. And you don't have these fast scale oscillations, these long mirror oscillations, but you do have the decay. And this decay is due to these fast oscillations in velocity space. Also at physical level, we see here there is something like a cascade of free transport. You can see this cascade, this idea of information going out in small scales, even when there is no interaction. If I look in Fourier space, Fourier in velocity, Fourier in position, here I'm in a periodic box setting, so the Fourier frequencies are discrete in the position space. And if I start in a configuration which is like this, then the evolution by free transport will be to make the high frequency modes in position go very, very far in the kinetic space. It is like a shear flow in the frequency variables. And this cascade, all the key in the Landau damping effect is to show that this cascade, already appearing in the linear case, survives the nonlinear perturbation. And this was the subject of a long paper that we wrote with Clément a few years ago. A key tool in the proof was to replace the statement that the force goes to zero, that you don't really know where it would come from, by a statement of propagation of regularity in some carefully designed spaces. This propagation of regularity is something kind of problem we are used to in partial differential equations. And it was the key of the interpretation. I like to say at this point that regularity exists. It looks provocative, but it's intended in particular for people who think that regularity is just an invention of mathematicians. Here in this problem, not only is it understood to drive the Landau damping in a bit the same way as regularity drives the decay of Fourier coefficients in the Riemann-Lebesgue lemma, but also it can be measured in a way in the sense that the regularity of your datum will have an influence of the rate of decay of the energy. It's like this Vlasov equation would be some kind of approximate way to Fourier transform the initial data and to look at the result in the exponential or not exponential decay of the electric field in time. A key step in the proof is to analyze the linear equation, linear transport equation, in which the force is unknown, corresponds to an unknown distribution, and it acts on a known distribution f bar that you give yourself, which is not stationary. If you believe that regularity is the key, the only assumption that you put on this f bar is that it has a certain regularity in a convenient scale of spaces. You try to look at the evolution of the density, say, for instance, the physical density rho, which would be the velocity integral, and try hard and get some integral estimate of Grunwald type. And you look at the kernel, how the evolution at time t is affected by the evolution for times that are before, and you find that you are in bad shape because the kernel is linear in time. This is very bad news because linear in time kernel seems to indicate exponential t-square growth. It's complete disaster. However, if you make a refined analysis of the kernel, you find that as time goes, it concentrates on earlier times which are more and more discrete. It looks weird, but to predict the evolution at time t, it's more important to know how was the gas at time t over 2 than to know how it was just a second before time t. This is due to compensations by oscillations, except in some case of kind of resonances. It resembles the Malmberg-Wharton experiment, famous experiment in plasma physics, in which you start with the plasma at rest, you send a pulse, see the effect on the electric field, wait until it rests, send a second pulse at a different frequency, wait again, and observe a spontaneous response of the plasma later, which is called the echo. From this experiment, we understand that plasma is a strange object in the long term, which reacts with delay. And this is an extremely important observation because delay is stabilizing. To convince ourselves of this, we can see the following baby models like Grunwald-type equations with a linear kernel there and a disastrous growth. Here, linear only in the integral sense, and you spread it over the integral. And here, linear again, but you concentrate all the mass of the kernel of the half-time, then the growth is much, much slower, like t to the power log t. I will conclude in an instant to mention first that this, in the case of plasmas, it will be more complicated than this, but it looks a bit like this. And you have a critical growth of exponential t to the 1/3, and this will correspond to a critical regularity in the analysis of the Vlasov equation. And in the end, you overcome this loss of regularity by a Newton scheme in the style of Kolmogorov. Let's skip this. And in the end, with this parallel that you can make, three of the most famous paradoxes of modern classical physics are related: Kolmogorov, plasma echoes, and Landau damping. That being said, only in the nonlinear regime, which is ironic because Landau was only considering the linear regime. And there is this dictionary, in the end, between the first story that I told about Kolmogorov-Arnold-Moser and the story of nonlinear Landau damping. And you can make connections between the two stories, even though they are very different systems. In one case, the enemy is the interaction, resonances between planets. In the other case, it would be resonances between plasma waves. And I will conclude by saying that using the same ideas and methods, Bedrosian and Masmoudi were able to solve a problem which was open for more than 100 years about the long time stability of a shear flow, linear shear flow that you slightly perturb, and you want to know if it will converge to a shear flow again in large time. The answer is yes. And again, this is related to this story which I started with Kolmogorov, continued with Landau, etc. Thank you very much.